All right, let's get into the execution of the relaxation method here so that we can start to figure out what these reactions are and then a shear moment diagram and the deflected shape and important features of those. All right, 35-meter span, 29.2 kilonewton per meter load. We're assuming that we have linear elastic behavior, that we have constant beam stiffness along the beam length, and that we do have this uniformly distributed load that doesn't change its magnitude and is applied everywhere along the length of the beam. All right, so let's go take a look here and verify that we do have a statically indeterminate system. We've got for potential reactions, a vertical at the left, an axial and a bending moment, and we have a vertical at the right. Hey, why don't we get some designations in here? We'll call the left A and we'll call the right B. So when we go add up all of our reaction components, we have 4. We have 2 dimensions, so we have 3 equations of equilibrium plus no special conditions. So our total number of equations is 3, and 4 is greater than 3 by 1, so therefore we're at a statically indeterminate to the first degree type of situation. One redundant reaction is what we have. Right, so what we're going to do in our strategy is that we're going to relax one of these redundant reactions. Now there's some sort of limit here. What we have to have is a stable system when we're done with this relaxation strategy. So for instance, if you were to select as our redundant reaction, then AX, we would have a roller and a pin and a roller. That would not be, or would we? No, we wouldn't. I selected AX. All right, so that's not what we have here. Instead, what that means, that mistake was actually on purpose to sort of help illustrate what we're really doing. We're getting rid of that restraint that is the X direction. So we don't have any resistance to movement left and right here. We do up and down, and we have a flexural resistance, but nothing here. And this is unstable, right? Because if there were a horizontal load, then that thing would slide and we wouldn't be able to do anything with it. So if we were to select the moment at A as an option, then we get the simple beam, or we could select the reaction at B. Those are the 3 possible systems. Well, one of them is not really possible, so we can choose either one of these as a redundant reaction. I like to work with cantilevers. You might like to work with the simple supported beam. I don't care which one you use. It's the same overall approach. So if we select BY, though, here's what's going to happen. We're going to have our original system with its uniform load on it. And we're going to temporarily get rid of BY. So now it's just the cantilever beam. We're going to put the original load on there. And when that happens, you're going to have a deflection that's going to then result in a displacement. So the beam deflects, and we will have a displacement at B that happens when you have no reaction there, right? And of course, it's happening in the downwards direction or negative direction. So let's go back up here. Originally, delta B is 0, and we'll call upwards positive, as we might normally do. Right? So then we got to get that back into place. And that's what both the relaxation method is all about. Relax that reaction and then put it back into place. That's why we will call it also the method of consistent deformations, because to make that happen with that unknown value of Vy, we have to have then mathematically a displacement out here that's caused by that reaction that comes back, and that will be in a positive direction, right? And the superposition is that in the original, these two must, of these two parts, must add up to the original. And since we had 0 for the original, and the second one was negative, and the other one is shown as positive, then we'll be able to have these two balance each other, right? And what will turn out is that delta B0 will be a number, or be in terms of the load in EI and the span length, and the second one will be in terms of the unknown BY. And we'll solve for that unknown force, which is why it's sometimes called the force method. This displacement delta BB is usually calculated with setting BY temporarily to be 1, in which case that becomes what we call flexibility coefficient, hence the name the flexibility method as well.